Hello, welcome to Lecture 8 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to learn the extremely important concept of the chemical potential. Okay, so in Lecture 4, we consider two systems, A and B, that can interact, exchanging energy, and they are isolated from the universe. And we looked for the most probable energy of system A. And mathematically, that means the energy that maximizes the multiplicity of the total system, and that led to the notion of thermal equilibrium as being the condition where the energy of system A is the most probable. Now we poke a hole in the wall dividing the two systems to let them exchange not only energy, but also particles. And when two systems can exchange particles, we say that they are in diffusive contact. And when two systems are in diffusive contact, now the number of particles become a property of interest. So now we have two properties of state, energy and number of particles. And in the same way that the total energy is conserved, the total number of particles is also conserved because particles can go from A to B or from B to A, but they do not leave the total system. And now we can also build the multiplicity of the total system, which is now a function of two variables, UA and NA. So the multiplicity of the total system evaluated at UA and NA is the number of states of the total system having system A with energy UA and number of particles NA. So it's basically just an extension of the notion we learned in lecture 4. And in the same way, this multiplicity is given by the product between the number of states of system A having energy UA and NA and the number of states of system B that can combine with these states of system A so as to satisfy the condition that the total energy must be U naught and the total number of particles must be N naught. So this is the multiplicity evaluated at the complementary energy and complementary number of particles. So for example, let's suppose that the total energy is again 2 and the total number of particles is 5. And this is one possible state of the total system. It is composed of a combination of the state HH of A and the state HTT of B. So what is the property of this state? Remember that we are interested in the property of the system A. So we have to look at the blue part. In this case, the state of the total system has system A in a state with energy 0 because both coins are HH and number of particles 2 because we have two coins. But it could be that this coin migrates to system B and then the total system will be in this state. In this state, system A has 0 units of energy and only one particle, one coin. Or for example, in this state of the total system, system A has 1 unit of energy and 3 particles. So we can build a list of states of the total system, count how many of them will have system A with a given energy and number of particles, and then we have the multiplicity. And now we can ask the same question we asked in lecture 4. We can ask what is the most probable energy of system A? Well, it's the same answer. It is the energy with most states. In other words, it is the energy that maximizes the multiplicity of the total system. In other words, it is the energy satisfying the condition that the derivative of the multiplicity with respect to the energy is 0, because that's the point of maximum. And in the same way, we can ask the same question about the number of particles of system A. We can ask what is the most probable number of particles in system A. That's the number of particles with the largest number of states. In other words, it is the number of particles maximizing the multiplicity of the total system. So it is exactly the same condition, but now the derivative is taken with respect to the number of particles. So it is the same reasoning we developed in lecture 4, with the only difference that now the derivative must be a partial derivative, because the multiplicity is a function of two variables. So since this is the same condition that we found in lecture 4, when we do the mathematical development, in other words, when we take this derivative using the multiplicity of system A and B, in other words, we use a chain rule here, we reach the same conclusion. The conclusion is that the most probable energy satisfies the condition that the derivative of the entropy with respect to the energy in both systems are the same. And that motivated the definition of temperature. So temperature is defined in terms of the derivative of the entropy with respect to the energy, because that's the parameter that must be constant across the system in equilibrium. In other words, that must be constant across the system when system A or B has the most probable energy. So that's the condition of thermal equilibrium. Now, if we follow the same development for the number of particles, we find that the most probable number of particles satisfies the condition that the derivative of the entropy with respect to the number of particles must be constant across the system. So this is the condition characterizing diffusive equilibrium. In other words, it is the condition giving the most probable number of particles. And this condition motivates the definition of the chemical potential. So the chemical potential is defined in terms of the derivative of the entropy with respect to the number of particles, because that's the parameter that has to be constant across the systems in diffusive equilibrium. So the definition of chemical potential is analogous to the definition of temperature in the sense that both are parameters that express the condition of equilibrium. The temperature express the condition of thermal equilibrium, and the chemical potential express the condition of diffusive equilibrium. Temperature must be constant in thermal equilibrium. Chemical potential must be constant in diffusive equilibrium. Now, you probably noticed that we do not define the chemical potential just as the derivative of the entropy with respect to the number of particles. We also multiply it by the temperature. And we do that because we want the chemical potential to be a potential in units of energy. And temperature times the entropy has units of energy. And we also have a negative sign here. So you can understand this negative sign as being a convention that allows us to describe the dynamics of the system in a way that is similar to the conventional dynamics we know from other potentials. So we know that, for example, balls fall from a higher gravitational potential to a lower gravitational potential. In the same way, particles diffuse from the higher chemical potential to the lower chemical potential. And you can prove that by yourself. How we do that? We follow the same logic we followed in lecture 5. In lecture 5, we proved that energy flows from a system with higher temperature to a system with lower temperature, because this is the condition that increases the entropy of the total system. In other words, energy flows from a hotter to a colder system just because that's the most probable thing to happen. And we can follow the same idea now, expressing the entropy as a function of two variables, energy and number of particles, And you can prove by yourself that if you follow an analogous reasoning, you can prove that the entropy of the total system increases when particles flow from the system with higher chemical potential to the system with lower chemical potential, when the chemical potential is defined like this with the negative sign. And why does that happen? For the same reason that energy flows from a hotter to a colder system, because that's the most likely thing to happen. And when you do this exercise, you can assume that the temperature is constant across the system. So from now on, we're going to focus attention on systems that are in thermal equilibrium. So from now on, we may assume that the temperatures are always constant across the systems. We are not interested in systems out of thermal equilibrium. We are more interested now in systems out of diffusive equilibrium. So let's summarize what we've learned. The characteristic of thermal equilibrium is that the temperature is constant across the system. Likewise, the characteristic of diffusive equilibrium is that the chemical potential is constant across the system. And when the systems are out of thermal equilibrium, then energy flows from the system with higher temperature to the system with lower temperature. Likewise, when the systems are out of diffusive equilibrium, particles flow from the system with higher chemical potential to the system with lower chemical potential. Now, we know that diffusion will happen when there is a difference in the concentration of particles. And now we learn that diffusion will happen when there is a difference in the chemical potential of the particles. So that can only mean that chemical potential and concentration of particles are intimately connected, and that is true. Later on in this course, we're going to find an explicit relationship between chemical potential and concentration of particles. But notice that they are not the same thing. Chemical potential, for example, has units of energy, and concentration doesn't have units of energy. But you can understand, it's useful to understand the chemical potential as being a measure of the concentration. So the higher the concentration is, the higher the chemical potential is. And the lower the concentration is, the lower the chemical potential is. So you can think of the chemical potential as being a measure of the concentration of particles. Another important physical meaning of the chemical potential is associated with the concept of free energy. But this is not absolutely important for the physics of semiconductor devices. So I'm not going to treat it in this lecture series, but you can find discussions and proofs of this assertion in the textbook. To conclude this lecture, we need to derive this expression that we're going to use next time. So delta here is again denotes a small variation. So what we want is to find an expression for delta S in terms of delta U and delta N. And to do that, we can use the expression from calculus. So this is the expression for a small variation of a general function of two variables. Then we use it for the entropy. Then the delta S is given by this contribution. This is just math, but we can bring the physical content, replacing the SDU with the inverse of the temperature, and the SDN with minus the chemical potential over the temperature. So this term becomes this, and this term becomes this. Then we isolate delta U, and we get the expression we want. So next time we're going to use it to investigate the interaction between chemical potential and other kinds of potential. And what we actually want is to understand how the chemical potential interacts with the electrostatic potential, forming the electrochemical potential or Fermi level. But we're going to begin by analyzing the interaction between the chemical potential and the gravitational potential, just because it's more intuitive. So we're going to start with the classic example of two gases interacting. We know that in equilibrium their concentrations must be the same, which means that the chemical potential is the same. But then we're going to ask what happens when one of the systems is placed at a higher gravitational potential. So I hope you have enjoyed this lecture, and I see you next time.